Right now, you're sitting inside the only confirmed system in the universe where every single protective condition aligned simultaneously. The stable, ancient star, the giant planet acting as a silent shield, the moon born from catastrophe, the magnetic field running invisibly beneath your feet. We've confirmed over 5,500 worlds out there, and not one sits inside an architecture like this. Tonight we walk through every condition that had to survive, in sequence, without a single failure for you to be here. Get somewhere comfortable, hit subscribe if you have not, and stay with me. Because after tonight, you will never see Earth the same way again. Not the sky, not the ground beneath your feet, not the moon hanging up there looking ordinary. None of it will look ordinary anymore. Let's get into it. Part 1. The Comfortable Lie. Here is something nobody tells you when you're sitting in a chair, looking out a window at an ordinary afternoon sky. Everything around you is the product of a chain of events so specific, so improbable, and so interdependent that the universe has apparently only managed to assemble it once in every collection of thousands of star systems we've ever studied. The air you're breathing right now, the stable pressure of it, the warmth carried in it, the fact that it hasn't been stripped away into space is not a default condition of rocky planets. It is a consequence of dozens of things going exactly right, in the exact right sequence, over 4.6 billion years. And we have now looked at enough of the universe to start understanding just how rarely that happens. Let's start with what you are actually sitting inside, because most people have a version of this in their head that is quietly, profoundly incorrect. You are on a planet that orbits a star that has been burning at almost the same luminosity for billions of years, varying by less than 0.1% over the course of an 11-year cycle. You are orbiting at a distance that keeps liquid water on your surface. You have a planet roughly 318 times your own mass, sitting out at 5.2 astronomical units, quietly reshaping the gravitational landscape of the outer solar system and deflecting objects that would otherwise find their way toward you. You have a moon that is, relative to Earth, the largest natural satellite of any rocky planet in the solar system, and it is holding your axial tilt steady within a narrow range that keeps your seasons predictable. Beneath your feet, thousands of kilometers down, liquid iron is churning in ways that generate a magnetic field strong enough to deflect the continuous stream of charged particles pouring out of your star. And the outer shell of your planet is broken into moving plates that have been cycling carbon through the atmosphere, ocean, and rock for longer than complex life has existed, acting as a thermostat that prevents the runaway warming that consumed Venus and the freezing collapse that took Mars. That entire description, every element of it, is a single system, not a collection of separate lucky features, but an interlocking chain where each component depends on or amplifies the others. The magnetic field helps retain the atmosphere. The atmosphere regulates surface temperature. Plate tectonics stabilize the long-term carbon cycle that keeps the atmosphere from tipping into runaway states. The moon stabilizes the tilt that keeps the seasons from going chaotic. Jupiter's gravity shaped the asteroid belt and the debris field that the early Earth was navigating, and the star's stability gave all of these processes the time they needed to work. Now, here is where things get interesting. As of 2025, we have confirmed more than 5,500 exoplanets orbiting stars other than our Sunday. We have catalogued more than 4,000 planetary systems. We have found planets orbiting ancient stars, young stars, binary stars, stars a fraction of the sun's size, stars many times more massive, planets made of rock, of gas, of something in between, planets that orbit their stars in less than a single Earth day, planets floating freely through interstellar space without any star at all. We have, in other words, sampled the galaxy's planetary inventory with a thoroughness that would have seemed like science fiction 30 years ago. And in all of that, in all 5,500 confirmed worlds, across more than 4,000 systems, we have not found a single confirmed system that mirrors the full architectural package of our own. Not one. Let that settle for a moment, because this is the thing that the scientific community of the 1990s did not predict. When astronomers first began theorizing about what exoplanet systems would look like, the working assumption was essentially that our solar system was typical. You form a star, material collapses into a disk around it, the inner disk produces rocky planets, the outer disk produces gas giants, things settle into roughly circular orbits, and you get something that looks broadly like home. The expectation was that the Milky Way was full of solar systems, in the most literal sense of that phrase, systems that looked like ours. What we found instead was so different that it forced a complete rethinking of planetary formation theory multiple times. Here is the conceptual move that matters most for understanding what we're doing in this video. When people hear that planets are common, and they are genuinely very common, most stars appear to have at least one planet. There is a natural tendency to conclude that Earth-like conditions must also be common. If planets are everywhere, surely Earth-like planets must be abundant too, and surely systems like ours must be abundant too. This is the comfortable lie. It treats each component of our solar system's architecture as though it exists independently, as though you just need to roll a single favorable die and you're done. But the architecture that produced Earth is not a single condition. It is a chain of conditions, each of which must be satisfied, and the probability of the chain is the product of the probability of each link. Think of it like a lock with 8 or 9 independent tumblers. Finding a key that aligns one tumbler is easy, but each additional tumbler you have to align multiplies the difficulty. And the universe, it turns out, almost never produces a key that aligns all of them at once. This is what we're going to walk through tonight. Not a catalogue of exoplanet facts, and not a meditation on whether life exists elsewhere, but a systematic examination of every condition that had to be satisfied for this specific architectural outcome to occur, and what the data tells us about how often each condition is actually met. We're going to go through the star, the formation history, the outer giants, the moon, the habitable zone, the magnetic field, the tectonics, and then we're going to multiply all of those probabilities together and look at what falls out of the other end of that calculation. Because here is the framing that I want you to carry through this entire video. We exist inside this system, which means we can only observe the universe from within a system that successfully completed the entire chain. We can't observe from a system that failed at step 3 or step 6. That's not a philosophical trick. It is a real constraint on how we interpret our own existence as evidence of anything about the universe. We are, almost by definition, going to find ourselves inside a successful outcome. The question is how many successful outcomes there are, and whether the night sky we're looking at is a common result of planet formation or something close to a cosmic accident. The answer, as the data currently stands, leans uncomfortably toward the latter. And understanding why is going to require starting not with Earth, not with Jupiter, not even with the solar system's formation, but with a star that you've never thought twice about, because it's been there every day of your entire life. Part 2. The architecture you memorized in school. Every version of our solar system you've ever seen in a textbook has a particular aesthetic to it. 4 small rocky worlds close in, a belt of rocky debris in the middle, and then 4 enormous planets, 2 gas giants, and 2 ice giants, arranged in a clean, layered sequence moving outward. It looks almost designed, orderly, intuitive. The kind of arrangement that makes sense when you think about how a spinning disk of material around a young star would naturally sort itself by density, with the heavy stuff falling toward the center and the lighter material drifting outward. This picture is not wrong. Our solar system does look that way, Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune. The orbits are very nearly circular, tilted by only small amounts relative to each other, all rotating in the same direction as the Sun's own spin. It is, by the standards of what we now know planetary systems can look like, a remarkably well-behaved arrangement. What the textbook version obscures is how strange this actually is once you look at everything else the galaxy has produced. When the first confirmed exoplanets around Sun-like stars were detected in the 1990s, and the story of that detection is worth a moment of attention, because it changed everything, what astronomers found was not a planet orbiting at a comfortable distance in a nearly circular path. What they found was a planet roughly the mass of Jupiter orbiting so close to its star that a year there lasted 4 Earth days. 4 days. The planet, designated 51 Pegasi b, was completing a full orbit around its star in the time it takes most people to notice that Monday came back around. It was enormous. It was hot, and it was right on top of its star in a way that no planet in our solar system comes close to replicating. And the question it immediately raised was, how did it get there? The answer, which took years to fully accept, was that it formed farther out where gas giants are expected to form, beyond what's called the snow line 3 message. The distance from the star, where temperatures drop enough for water ice and other volatile compounds to condense into solid particles and then migrated inward, planets move. This was not built into the original models of solar system formation in any significant way. The expectation had been that planets form in their disk, stay roughly where they form, and you get a stable configuration. What we found instead was that migration is not the exception. For many systems, it appears to be the rule. These close-in gas giants, hot Jupiters they're called, because surface temperatures of 1,000 degrees or more are common for something that close to a star appear in roughly 1% of the planetary systems we observe. That sounds rare, and it is, in the sense that you won't find one everywhere. But their existence alone was enough to indicate that planetary systems routinely undergo dramatic rearrangements from whatever initial state they form in. Then came the next surprise, and this one was bigger. When the Kepler Space Telescope began systematically cataloguing planets between 2009 and 2018, the most common type of planet it found was something that doesn't exist in our solar system at all. A planet between 1.5 and 3.5 times the radius of Earth, too large to be a simple rocky world, not large enough to be a gas giant. These are variously called super-Earths or sub-Neptunes, depending on their exact size and density, and they are everywhere. They orbit around something like 30 to 40% of all Sun-like stars. They are, statistically speaking, the galaxy's most typical planetary output. If you want to know what an average planet looks like, it probably looks something like this: bigger than Earth, smaller than Neptune, orbiting relatively close to its star. Our solar system has 0 of these. There is actually a name for the region of planetary size where these worlds cluster. It's called the Fulton Gap, a statistical dearth of planets with radii between roughly 1.5 and 2 Earth radii. Below that size, you get rocky planets. Above it, you get gas-rich sub-Neptunes. The gap itself is thought to be caused by atmospheric evaporation. Planets in that intermediate size range tend to lose their atmospheres when they're close enough to their stars, leaving behind a bare rocky core. This gap appears consistently in the Kepler data and has been confirmed in subsequent surveys. It's a real feature of the planetary population. And our solar system's 4 inner planets sit on one side of that gap, and our 4 outer planets sit completely outside its domain and nothing in between. This is not a minor difference. This is not a case where our solar system is slightly unusual on one parameter. The most common class of planet in the galaxy is absent from our system entirely, and the explanation for that absence takes us directly into the formation history of the solar system, a history that, as we're going to see, involved Jupiter doing something extraordinary in its youth that permanently altered what the inner solar system was capable of producing. But before we get there, it's worth sitting with the broader picture of what exoplanet surveys have shown about orbital architecture, because the contrast with our system goes beyond just planet types. Compact multi-planet systems, where several planets orbit very close to their star, often within the distance that Mercury sits from our Sun, are common. Highly eccentric orbits, where a planet swings wildly close to and then far from its star in an elongated ellipse rather than a near circular path, are common. Systems that show evidence of past gravitational instabilities, where planets have scattered each other into new orbits or been ejected from the system entirely, are common. By essentially every metric of orbital behavior, our solar system's configuration is unusual. The low eccentricities, the coplanar alignment, the clean separation between the inner rocky worlds and the outer giants. These are not the typical outcomes that planetary formation produces. The architecture itself is the first filter. The question is why we ended up on the right side of it, and that answer starts in violence. Part 3. The first crack. Our star is not typical. Before we can talk about how planets form and what determines the architecture of a solar system, we have to talk about the thing that everything else orbits, because the star is not background context. The star is the filter. In many ways, it is the most important filter of all, and it is the one that most people walk past without a second thought, because they've spent their entire lives inside a system that happened to get it right. The Sun is a G-type main sequence star. That classification means it sits in a particular band of stellar mass, temperature, and luminosity. Not the biggest, not the smallest, not the hottest, not the coolest. It burns hydrogen in its core through nuclear fusion, converting roughly 600 million tons of hydrogen into helium every second. And it has been doing this with extraordinary consistency for 4.6 billion years. Its luminosity varies by roughly 0.1% over the course of its 11-year magnetic activity cycle. In terms of stellar behavior, the Sun is about as quiet and stable as a star gets. Here is the thing about that. G-type stars like the Sun make up somewhere between 7 and 8% of all stars in the Milky Way. 7 to 8%. The most common stars in the galaxy, by a very large margin, are M-type stars, also called red dwarfs or M-dwarfs. They account for somewhere between 75 and 80% of all stars. They are smaller, cooler, and dimmer than the Sunday. A typical red dwarf might have half the Sun's mass, a third of its diameter, and emit perhaps 1% of the Sun's luminosity. They burn their fuel so slowly that many of them will still be fusing hydrogen trillions of years from now, long after the Sun has expanded into a red giant and incinerated everything within the inner solar system. So if you are randomly assigned a planet in the Milky Way, it is far more likely to be orbiting a red dwarf than any other type of star. Which means the question of whether red dwarf systems can support complex life is not an academic one. It is probably the central question for the frequency of life in the galaxy. And here is where the story gets complicated, in a way that matters directly for our central question about how rare our solar system's architecture truly is. Red dwarf stars are active. Not occasionally active, many of them are routinely, aggressively active in ways that dwarf anything the Sun produces. They emit X-ray and ultraviolet radiation bursts, called flares, that can, in the worst cases, exceed the Sun's total output across all wavelengths during an equivalent flare by factors of hundreds or even thousands. A powerful flare from a red dwarf can deliver more radiation to its nearby planet in a matter of minutes than that planet receives from stellar radiation in an entire day under calm conditions. And the habitable zones of red dwarfs, the distances from the star where liquid water could theoretically persist on a planet's surface, are very close in, because red dwarfs are so much dimmer than the Sunday. A planet would need to orbit at perhaps 1/10 to 1/5 of the Earth-Sun distance to receive enough warmth to stay liquid. Being that close to a star creates its own problem, entirely separate from the flaring, tidal locking. When a planet orbits close enough to its star, the star's gravity differentially pulls on the near and far sides of the planet, gradually slowing the planet's rotation until it stops rotating relative to the star entirely. One side of the planet permanently faces the star, the other permanently faces away. You get a world with a permanently blazing hemisphere and a permanently frozen one, with extreme temperature gradients and atmospheric circulation patterns that have no analogue in our experience. Whether a tidally locked planet with active flaring could maintain a stable atmosphere, let alone liquid water, is genuinely unknown. The models give different answers depending on what you assume about the planet's initial atmospheric composition, its magnetic field strength, and the severity of the flaring history. Some models suggest that thick enough atmospheres could redistribute heat efficiently enough to maintain habitable conditions on at least part of the planet's surface. Others suggest the flaring alone is sufficient to strip the atmosphere over geologically short timescales. The closest thing we have to an observational test is Proxima Centauri b, a planet roughly 1 to 1.3 times Earth's mass, orbiting Proxima Centauri, the nearest star to the Sun, at a distance that puts it squarely in the star's habitable zone. Proxima Centauri is a red dwarf. It flares. Proxima b is almost certainly tidally locked. Whether it has an atmosphere at all is currently unknown. The James Webb Space Telescope has attempted to characterize it and has not yet produced a definitive answer. The planet is technically in the right place. Whether it is anywhere close to the right conditions is a completely open question. This uncertainty is itself the point. The Sun gives Earth something that is genuinely unusual among stellar environments: consistent, stable, long-duration energy delivery without the extreme variability of flaring at a distance that doesn't require tidal locking. The Sun has been doing this for 4.6 billion years, and it will continue doing it for roughly another 5 billion. That timescale matters, because the development of complex life on Earth, from single-celled organisms to multicellular life, took something like 3 billion years. Complex animal life, by the fossil record, has existed for roughly 600 million years. Intelligence of the kind that builds radio telescopes and exoplanet surveys has existed for perhaps 100,000. A star that is too volatile or too short-lived doesn't give biological processes the time they need. And many stars, including many G-type stars, simply don't live long enough in their stable phase to permit the full sequence. The Sun is in a sweet spot not just of temperature and luminosity, but of lifetime and stability. There is one more factor worth mentioning here, and it is one that rarely makes it into popular accounts: the Sun's position in the galaxy. The Milky Way is not uniform. Stars in the galactic center are densely packed and frequently subjected to supernova explosions, gamma-ray bursts, and intense radiation from the region near the central black hole. Stars in the outer galaxy may be so metal-poor, so deficient in the heavy elements, that form rocky planets, that Earth-like worlds may simply not be possible. The Sun sits in a relatively quiet region of one of the galaxy's spiral arms, far enough from the center to avoid the worst of the radiation environment, but close enough that heavy elements from earlier generations of stellar explosions were available to build rocky planets. This position may itself be part of the filter. So before we've even talked about planets, we've already established that the star we orbit is unusual. It is a minority class of star. It is exceptionally stable. It is long-lived. It is positioned in a favorable region of the galaxy. Each of these properties narrows the field of candidate systems for producing something like Earth. And we haven't even gotten to the formation history yet, which is where things get genuinely strange. Part 4. The birth, the that nearly went wrong. 4.6 billion years ago, in a region of the Milky Way, unremarkable in almost every way, a cloud of gas and dust that had been floating in something close to equilibrium for millions of years began to collapse. Something disturbed it. The shockwave from a nearby supernova explosion is one leading candidate, and gravity did the rest. The cloud contracted. Conservation of angular momentum caused it to spin faster as it shrank, and eventually what you had was a hot, dense protostar, surrounded by a rotating disk of gas and dust extending out for hundreds of astronomical units. The solar system had begun assembling itself. The disk had structure from the beginning. Temperature decreased with distance from the protostar, and that temperature gradient determined what could exist in solid form at different distances. Close in, within roughly the first 2 to 3 astronomical units, it was simply too hot for water, ice, methane, ammonia, or any of the volatile compounds to remain solid. Only materials with high melting points, silicates, iron, nickel, could survive in solid form. These are the ingredients of rocky planets, and the inner solar system's 4 planets are made of exactly this stuff. Farther out, beyond what planetary scientists call the snow line, located somewhere around 3 astronomical units in the early solar system, roughly where the asteroid belt now sits, temperatures dropped below the condensation point of water ice. Suddenly, the amount of solid material available in the disk increased dramatically because ice is far more abundant in the universe than silicates. The surface density of solid material in the outer disk was estimated to be several times higher than in the inner disk, and this abundance had a critical consequence. Planetary cores could grow much faster out there. Jupiter's core formed first, or so the core accretion model tells us. A rocky icy core, several times the mass of Earth, accumulated at around 5 astronomical units, and once it crossed a critical mass threshold of somewhere between 5 and 15 Earth masses, it began gravitationally pulling in the surrounding gas at an accelerating rate. The runaway gas accretion phase was geologically brief, perhaps a few 100,000 years, and at the end of it, you had a planet with more than 300 times Earth's mass, sitting at 5 astronomical units. Here is where the story takes a turn that permanently altered the fate of everything inside Jupiter's orbit. Planets don't stay where they form. This is the lesson that hot Jupiters taught us, and it applies to our own solar system in a way that we didn't appreciate until fairly recently. Jupiter formed, but forming doesn't mean staying. Interactions between the planet and the gas disk, the same disk that was still accreting onto the proto-sun, produced torques that cause the planet to drift. The direction and magnitude of that drift depend on the planet's mass and the disk's structure, and for Jupiter, the models say it drifted inward, not a little, a lot. The Grand Tack hypothesis, developed in the 2000s and refined over subsequent years, proposes that Jupiter migrated inward from roughly 5 astronomical units to approximately 1.5 astronomical units, well inside the current position of Mars, closer to where the asteroid belt sits today. If you're trying to picture this, Jupiter, at its most inward point during the Grand Tack, was not much farther from the Sun than Mars is today. This is a gas planet the size of 318 Earths, sitting where, in today's solar system, a small, red, rocky world lives. The consequences of this migration for the inner solar system were profound. Jupiter's gravitational influence swept through the inner disk region, stirring up and disrupting the material that was beginning to coalesce into what would have been the inner planets. The planetesimals and protoplanets that were in the process of growing into larger bodies got scattered, perturbed, and in many cases ejected. The mass that would otherwise have accreted into a large inner planet was systematically removed from that region. This is, according to the Grand Tack model, why Mars is so small. Mars is only about 1/10 of Earth's mass, and the expectation based on the available material in that region would be a planet significantly larger. Jupiter's passage through the inner solar system starved the Mars-forming region of material. But Jupiter didn't keep moving inward. Saturn formed in the outer disk, also migrating inward, but more slowly. When Saturn's orbital period came into a precise 2 to 3 resonance with Jupiter's meaning, Saturn completed exactly 2 orbits for every 3. Jupiter completed the gravitational coupling between the 2 planets, reversed their migration. Instead of moving inward, they began moving outward. Jupiter tacked, like a sailboat changing direction into the wind, and retreated back toward the outer solar system. It settled into something close to its current orbit. The grand tack neatly explains several features of our solar system that are otherwise difficult to account for simultaneously. The small mass of Mars, the mass and compositional distribution of the asteroid belt, and the fact that the inner solar system has no super-Earths, despite being a region where they frequently form in other systems. Jupiter's inward migration and subsequent retreats prevented the kind of mass accumulation in the inner disk that produces super-Earths. Our solar system avoided that outcome not because the conditions for super-Earth formation were absent, but because Jupiter intervened. The grand tack is not universally accepted. Alternative models exist that explain some of the same features through different mechanisms. But all of the leading models agree on the basic point. Jupiter's formation and migration history had a decisive influence on the structure of the inner solar system. The specific outcome, we see 4 small rocky planets with low eccentricities and no super-Earths, is not the default result of rocky planet formation. It is the result of a particular history with a particular giant planet doing particular things at a particular time. If Jupiter had formed more slowly and missed the migration window, if Saturn had formed at a slightly different time and the resonance that reversed Jupiter's migration had been missed, if the disk had a different density profile, shifting the snowline and changing Jupiter's formation location, any of these variations likely produces a different inner solar system. One with a more massive Mars, or with super-Earths closer to the Sun, or with no stable habitable zone planet at all. And then, roughly 600 to 800 million years after the solar system formed, when you might think the drama was over, things went wrong again. The NICE model, named after the city in France where it was developed, not the adjective, describes a second major rearrangement of the outer solar system that is thought to have occurred around 3.9 billion years ago. The outer planets, Jupiter, Saturn, Uranus, Neptune, were initially in a more compact configuration, with the orbits closer together than they are today. The interaction between these planets and a primordial disk of smaller icy bodies in the outer solar system eventually destabilized this arrangement. Neptune migrated outward, Uranus migrated outward. Saturn and Jupiter settled into a near 2-to-1 resonance before breaking out of it. The rearrangement sent a pulse of material inward toward the inner solar system. This event may correspond to what the geological and lunar record calls the late heavy bombardment, a period approximately 3.9 billion years ago when the lunar surface, and presumably Earth, experienced an elevated rate of large impact events. The evidence for the late heavy bombardment is read from the ages of impact melt rocks brought back by Apollo missions, which cluster around that time in a way that suggests something exceptional was happening. Whether it was a genuine spike in impact rate or simply the tail end of the earlier formation bombardment is still debated, but the broader point stands. Even after the initial formation drama of the grand tack, our solar system experienced a major outer planet rearrangement that sent shock waves through the entire system. Our solar system survived that too. The chain of contingencies that had to work out correctly, Jupiter forming at the right time, in the right place, migrating inward by the right amount, being stopped by Saturn's resonance, retreating back to the outer solar system, the NICE model rearrangement occurring without ejecting any of the planets, is exactly the kind of chain that the central argument of this video is built on. Each link is necessary. Each link was not guaranteed. How many systems attempt this path and fail at one of these junctions? We don't know, because we can't directly observe the formation histories of other systems. But we can ask how common Jupiter analogues are. We can ask what happens to inner systems in the absence of the right kind of outer giant. Both of those questions take us directly to the planet that may be the most consequential single object in our solar system outside of Earth itself. Part 5. The Silent Protector. Let's talk about Jupiter, because Jupiter has a job description that most people have never seen written down, and understanding that job is essential for understanding why the architecture of our solar system is genuinely unusual in a way that goes beyond formation history. Jupiter is the largest planet in the solar system. Its mass is 318 times Earth's mass. Its diameter is 11 times Earth's diameter. If you hollowed out Jupiter and filled it with Earths, you could fit more than 1,300 of them inside. It sits at 5.2 astronomical units from the Sun, completing one orbit every 11.9 Earth years. In an orbit that is very nearly circular, its eccentricity is only about 0.05 compared to Earth's 0.017. In the context of what we see elsewhere in the galaxy, both of these properties, the near-circular orbit and the position at 5+ astronomical units, are relatively rare for a Jupiter mass planet. The gravitational influence of a planet the size of Jupiter at a distance of 5.2 astronomical units is substantial and extends throughout the solar system in ways that are not always intuitive. Jupiter's gravity is the dominant non-solar gravitational influence on virtually everything in the solar system. The asteroid belt, the Kuiper belt, long-period comets on highly elliptical orbits, and the trajectories of small bodies that wander into the inner solar system from the outer regions. The classic framing of Jupiter's role, what has been called the Jupiter as shield hypothesis, is that Jupiter deflects and ejects objects that would otherwise impact Earth at a much higher rate. The mechanism is straightforward in principle. Comets and asteroids falling into the inner solar system on dangerous trajectories encounter Jupiter's gravity first, and Jupiter's gravitational influence scatters them. Many are redirected into orbits that take them out of the inner solar system entirely. Some are captured into Jupiter's vicinity and eventually impact Jupiter itself. We have actually watched this happen. In July of 1994, comet Shoemaker-Levy 9, which had been torn apart by Jupiter's tidal forces into a chain of fragments, impacted Jupiter over the course of several days. The largest impacts created scars in Jupiter's cloud tops larger than Earth. The energy released was estimated in the hundreds of millions of megatons. If those impacts had happened on Earth instead of Jupiter, they would have been civilization-ending events. The quantitative extent of Jupiter's shielding effect has been revised considerably over the decades. Early estimates suggested that without Jupiter, Earth's impact rate from comets could be 10 to 1,000 times higher. More recent simulations have complicated this picture. Some models suggest Jupiter is simultaneously a shield and, in certain configurations, an amplifier, that its gravity can also redirect objects toward Earth that would otherwise have stayed safely in the outer solar system. The net effect appears to depend sensitively on the details of Jupiter's orbit and mass, and the consensus today is that Jupiter's protective role is real, but probably less dramatic than the 10 to 1,000 times estimate. The honest answer is that the exact magnitude of the effect is uncertain, but the direction of it, that Jupiter's presence meaningfully reduces the impact hazard in the inner solar system compared to a system without a comparable outer giant, appears robust. What's not uncertain is the rarity. Jupiter analogues giant planets with masses comparable to Jupiter's, orbiting beyond 3 astronomical units in roughly circular orbits, are found around only about 6 to 10% of Sun-like stars. 6 to 10%, and that's just counting the existence of the analogue. The additional requirement that Jupiter be at the right distance far enough out that it doesn't migrate inward and destabilize the inner system, close enough that its gravitational influence still shapes the outer debris disk, effectively adds another layer of specificity. Hot Jupiters, the close-in gas giants that formed in the outer disk and then migrated all the way into sub-1 AU orbits, are thought to have devastated the inner planetary systems of the stars they orbit. The migration of a Jupiter-mass body through the inner solar system sweeps up or ejects whatever rocky planets were forming in that region. The habitable zone of those systems likely gets cleared. The analogy is a wrecking ball being dragged through a construction site. So the requirement is not just has a Jupiter-mass planet, but has a Jupiter-mass planet that stayed in the outer solar system and didn't migrate destructively inward. The grand TAC model we discussed earlier gives us a specific example of how close our own system came to the hot Jupiter outcome. Jupiter did migrate inward. It stopped and reversed. The reversal was contingent on Saturn's formation and the establishment of a gravitational resonance at exactly the right time. What fraction of systems with Jupiter-mass outer giants successfully negotiate this migration and reversal rather than producing a hot Jupiter? We don't know precisely, but the rarity of true Jupiter analogues versus the observed frequency of hot Jupiters and systems without any giant planet at all suggests the answer is something like a small minority. Jupiter is not simply an oversized planet sitting in the outer solar system minding its own business. It is an active gravitational architect of our entire solar system, and the specific form that architecture took, the one that gave Earth a stable, relatively low-impact environment over billions of years, required Jupiter to be exactly the right size, in exactly the right place, behaving in exactly the right way during the formation epoch. Any of those parameters shifted significantly, and the inner solar system might look profoundly different. This is one of the threads running through the entire architecture of our solar system. Conditions that look like fortunate accidents, when you examine them individually, form a network of mutual dependencies when you examine them together. Jupiter's orbit was shaped by Saturn. Saturn's influence on Jupiter was shaped by the structure of the primordial disk. The disk's structure was shaped by the sun's luminosity and the position of the snow line. Each thing connects to every other thing, and the specific combination we ended up with is, as far as we can tell from the data, uncommon. The next link in the chain is one that involves catastrophe, transformation, and a collision that happened 4.5 billion years ago but is still keeping your seasons stable today. Part 6. The collision that made stability possible. The moon is the most taken-for-granted object in the night sky, and it may be the most consequential accident in the history of the solar system. The leading hypothesis for the moon's formation, the giant impact hypothesis, now supported by a substantial body of evidence from lunar rock analysis, isotopic ratios, and dynamical modeling, says that roughly 4.5 billion years ago, the early Earth was struck by a Mars-sized body. This object, which planetary scientists have named Theia after the Titan mother of the moon in Greek mythology, collided with proto-Earth at an oblique angle in a massive, glancing impact. The collision was not a head-on collision. If it had been, the energy release might have vaporized both bodies entirely. Instead, the oblique geometry meant that Theia's outer layers were largely sheared off and ejected into orbit around Earth, while Theia's iron core merged with Earth's. The debris that entered orbit gradually coalesced under its own gravity into the moon. The evidence for this model is strong but not perfect. The moon's composition is extremely similar to Earth's mantle composition. The two bodies share almost identical oxygen isotope ratios, which is the kind of geochemical fingerprint that points to a common origin. The moon has a small iron core compared to its size, consistent with the idea that most of the iron in the impacting body ended up in Earth's core rather than in the moon. And the angular momentum of the Earth-Moon system is consistent with the kind of oblique impact the model describes. One of the consequences of this impact that doesn't always get enough attention is the moon's effect on Earth's axial tilt stability, and this is where the story connects directly back to our central thread. Earth's axial tilt, the angle at which Earth's rotational axis is tilted relative to its orbit around the Sun, is currently about 23.5 degrees. This tilt is what gives us seasons. When the northern hemisphere is tilted toward the Sun, it receives more direct sunlight and experiences summer. When it's tilted away, it receives less direct sunlight and experiences winter. Without axial tilt, you'd have no seasons, just a perpetual climate at each latitude determined entirely by distance from the equator. The specific value of the tilt matters less than its stability over time, and here is where the moon becomes critically important. The gravitational interactions among the planets, particularly the pull of Jupiter and the other giant planets on Earth's equatorial bulge, are constantly trying to perturb Earth's axial tilt. Without the moon, models suggest that Earth's axial tilt would wander chaotically over a very wide range, possibly anywhere from near zero to nearly 90 degrees over timescales of tens of millions of years. At 90 degrees of axial tilt, one pole of the planet would point directly at the Sun for half the year and directly away for the other half. The climate consequences would be catastrophic. Polar regions would experience months of continuous direct sunlight. Mid-latitude regions would see temperature swings of hundreds of degrees over the course of a year, and the ice albedo feedback, where ice reflects sunlight and cools the surface, which makes more ice, could push the planet into or out of global glaciation episodes unpredictably and rapidly. The moon stabilizes this. The moon's tidal coupling with Earth's equatorial bulge exerts a torque that keeps Earth's axial tilt precessing slowly rather than wandering freely. The result is that Earth's axial tilt has varied only between about 22.1 and 24.5 degrees over the past few million years, a variation of about 2.5 degrees over cycles of roughly 41,000 years. This is small enough that its climate effects, while measurable and important for the timing of ice ages, don't fundamentally alter the habitability of the planet. Mars is the comparison case. Mars has two tiny moons, Phobos and Deimos, that are far too small to provide any meaningful stabilization of its axial tilt. Mars's axial tilt has likely varied between 0 and about 60 degrees over its history. The climate record, preserved in Martian geology, shows evidence of these dramatic variations, ancient river channels that formed when conditions were warmer and wetter, followed by eras of extreme cold that drove any liquid water beneath the surface or into ice deposits near the poles. Whether any of this is connected to axial tilt variations specifically is still being researched, but the dynamical instability of Mars's tilt is established. Now consider that the probability of a giant impact producing a moon large enough to stabilize axial tilt, as opposed to a smaller moon that provides partial stabilization, or a collision that doesn't produce a stable moon at all, or a collision that occurs at the wrong geometry and vaporizes the planet's oceans, is estimated by some researchers at around 5 to 10% for Earth-like planets that experience large impacts. And the probability of the right-sized giant impact occurring in the first place is not 100% either. Many planets form without undergoing any late giant impacts. Many giant impacts produce debris disks that don't coalesce into a stable moon. The specific outcome, the moon we have, at the size it is, doing the stabilizing it, does require a particular kind of collision, at a particular energy and angle, followed by a particular disk evolution. A collision 4.5 billion years ago is still holding your axial tilt steady today. That connection between a catastrophic event in the solar system's early history and the mild, predictable seasons that made agriculture possible and complex civilization possible is the kind of thing that is genuinely difficult to fully appreciate without stopping and sitting with it for a moment. And yet this is still only partway through the chain. We have a stable star, a Jupiter in the right place, a moon providing tilt stability. We still need to talk about the habitable zone itself and why being in it is not even close to being the end of the story. Part 7. The misleading simplicity of the habitable zone. The habitable zone, the Goldilocks zone, the region around a star where liquid water could theoretically exist on the surface of a planet. This concept has been at the center of the search for Earth-like worlds since the 1960s, and it has been, in many ways, both the most useful and the most misleading idea in astrobiology. Here is the useful version. The habitable zone is defined as the range of orbital distances at which a planet with Earth-like atmospheric composition would maintain surface temperatures between 0 and 100 degrees Celsius. The liquid water range. The inner boundary of the habitable zone is where the greenhouse effect would become a runaway process, causing the planet to heat until its oceans evaporate, and the resulting water vapor in the atmosphere amplifies the warming further, eventually driving the planet towards something like Venus. The outer boundary is where even a strong greenhouse effect from carbon dioxide buildup wouldn't be enough to prevent the surface from freezing permanently. For our Sun, the conservative habitable zone runs from roughly 0.95 astronomical units to 1.4 astronomical units. Earth is at 1 astronomical unit. We're in the zone. So is Mars, marginally, at its most optimistic estimates. Venus is just inside the inner edge. Here is where it gets complicated. These numbers assume Earth-like atmospheric composition, Earth-like atmospheric pressure, and Earth-like surface albedo. Change any of those, and the zone shifts. Venus, which is inside the conservative inner boundary for our Sun, has a surface temperature of around 460 degrees Celsius, hot enough to melt lead due to an extreme greenhouse effect from its carbon dioxide atmosphere. But Venus also has no liquid water, no plate tectonics cycling carbon through the system to moderate the greenhouse effect, and no magnetic field to speak of. Calling Venus in the habitable zone according to any definition that implies it might be habitable is a stretch of the concept to the point of meaninglessness. Mars sits near the outer edge of the optimistic habitable zone. It has water frozen in polar ice caps and in the subsurface permafrost, and evidence suggests it had liquid surface water early in its history. But Mars today has an atmospheric pressure less than 1% of Earth's, a mean surface temperature of around -60 degrees Celsius, and no active global magnetic field. It lost its atmosphere over billions of years through a combination of solar wind stripping and impact erosion. Whether Mars was ever truly habitable, and for how long, is an active research question, but its current state makes clear that being in the habitable zone does not automatically preserve habitability. The habitable zone is a starting constraint, not an ending condition. A planet needs to be in the zone. You can't have liquid water on the surface if you're so close to your star that you're being vaporized, or so far away that everything is permanently frozen. But a planet can be in the zone and still be uninhabitable for a dozen other reasons, and this is the misleading simplicity the concept carries with it. Let's add some of those additional constraints that the simplified habitable zone picture doesn't capture. Orbital eccentricity matters enormously. A planet in an eccentric orbit might spend part of its year within the habitable zone and part of its year significantly outside it, closer to the star, and dangerously hot for a few months, then far from the star and potentially freezing for a few months. The average might fall in the zone, but the extremes could prevent liquid water from being stable at all. Earth's current eccentricity of 0.017 is very low, our orbit is very nearly circular, and the difference in Earth's distance from the Sun between its closest and farthest points is only about 5 million kilometers. Many observed exoplanets have eccentricities of 0.3, 0.5 or higher. The habitable zone also shifts over time because stars evolve. The Sun today is roughly 30% more luminous than it was when the solar system formed 4.6 billion years ago. This means the inner boundary of the habitable zone has moved outward over time. Earth's surface conditions 4 billion years ago were being maintained against a considerably dimmer sun than we have today, a problem known as the faint young sun paradox, which asks how Earth avoided being frozen solid early in its history when the sun was so much dimmer. The answer involves a stronger greenhouse effect in the early atmosphere, likely involving higher concentrations of carbon dioxide and possibly methane. But this answer works partly because of plate tectonics, which was recycling carbon through the system and modulating the atmospheric concentration, and partly because of Earth's internal heat, which maintained the liquid water ocean that itself participated in the carbon cycle. A planet that happens to be in the habitable zone at one point in its star's evolution may not remain in the zone over geological timescales. Venus may have been in the zone early in the solar system's history, with a milder greenhouse effect and possibly even liquid water. As the sun brightened, the inner boundary of the zone moved outward past Venus, triggering a runaway greenhouse that made Venus what it is today. Earth avoided this only because its feedback mechanisms, the plate tectonics, the carbon cycle, the ocean chemistry, successfully moderated the greenhouse effect as the sun brightened. So the habitable zone is, at best, a necessary condition for surface habitability. It is very far from sufficient. And the list of sufficient conditions that we have to add to it, orbital stability, long-term atmospheric stability, appropriate greenhouse effect modulation, access to the right materials, time is long, and not all of it is visible from outside the system. This is what makes the search for Earth-like worlds so genuinely difficult, and why the discovery of a planet in the habitable zone is always followed, if you read carefully, by pages of caveats about all the things we don't know. Being in the zone is the first question. There are many more questions after it. Part 8. The invisible shields beneath your feet. There are two features of Earth that are almost certainly critical to its current habitability, that are almost impossible to detect on planets orbiting other stars, and that are, in the context of rocky planets generally, possibly quite rare. One is deep beneath your feet, the other manifests in the behavior of the planet's surface. Both of them have been operating, in one form or another, for billions of years, and together they may represent the hardest part of the chain to reproduce. Let's start with the magnetic field. Earth's magnetic field is generated in the outer core, a region of liquid iron and nickel extending from about 2,900 kilometers depth to about 5,100 kilometers depth. Heat flowing out of the inner core drives convection in this liquid iron, and the combination of that convection and Earth's rotation generates electric currents that sustain the magnetic field through a process called the geodynamo. The field extends from the surface of Earth out into space, forming the magnetosphere, a region of space in which Earth's magnetic influence dominates over the sun's. The magnetosphere's primary function, for our purposes, is to deflect the solar wind. The solar wind is a continuous stream of charged particles, mostly protons and electrons, flowing outward from the sun at speeds of around 400 kilometers per second. When this stream encounters Earth's magnetosphere, the charged particles are deflected around the planet, guided toward the polar regions, where they spiral down along magnetic field lines and produce the auroras. Without the magnetosphere, the solar wind would impinge directly on the upper atmosphere and gradually strip it away, a process called atmospheric sputtering. Mars is the object lesson in what happens without a magnetic field over geological timescales. Mars's core cooled, and its global dynamo shut down roughly 4 billion years ago, possibly as early as the late heavy bombardment period. Once the dynamo stopped, the magnetosphere collapsed. The solar wind then had direct access to the Martian atmosphere, and over billions of years it stripped much of that atmosphere away. Mars today has an atmospheric pressure less than 1% of Earth's, and what remains is almost entirely carbon dioxide. Any liquid water that might have existed on the early Martian surface, and there is significant geological evidence that it did, was no longer sustainable on the surface once the atmosphere was gone. The oceans, if they existed, froze or sublimated into space. The comparison is stark and direct. Earth has maintained a magnetic field for at least 3.5 billion years, possibly since very early in its history, and this has allowed it to retain a substantial atmosphere. Mars lost its field and lost much of its atmosphere. The causal connection is well established. What determines whether a rocky planet maintains an active dynamo over billions of years? The planet needs to have a large enough iron core. It needs to have an inner core that is partially or fully solid to drive the convection in the outer liquid layer through the release of latent heat as the inner core slowly crystallizes, and it needs to retain enough internal heat to keep the outer core liquid. All of these requirements are ultimately set by the planet's mass, composition, and formation history. Too small a planet loses its heat too quickly and its core solidifies. Too large a planet may have a different convective regime. The specific configuration that sustains an active geodynamo over billion-year timescales is not guaranteed. Venus is the interesting counterexample. Venus is nearly the same size as Earth, nearly the same mass, and almost certainly had a similar initial composition. And yet Venus shows no evidence of an active global magnetic field today. The reasons for this are debated, possibly Venus's slow rotation rate. It rotates once every 243 Earth days, and in the opposite direction from most planets, prevents the kind of core convection needed for a dynamo, or possibly Venus's core has already solidified. Whatever the reason, Venus demonstrates that a planet nearly identical to Earth in mass can fail to generate a protective magnetic field, and Venus has retained a very thick atmosphere anyway because it's close enough to the Sun that its thermal escape rate is manageable even without magnetic shielding, and because the greenhouse gases it has retained create enough pressure to resist sputtering. But Venus's retention of atmosphere, despite the lack of a magnetic field, may be the exception that proves the rule, a product of specific conditions that wouldn't apply at Earth's distance from the Sunday. Now let's talk about what's happening at the surface. Plate tectonics is the other invisible process that is likely critical for long-term habitability, and it is equally difficult to detect from outside the system. Earth's outer layer, the lithosphere, is broken into roughly a dozen major plates and several smaller ones, all moving relative to each other at speeds of a few centimeters per year. At the boundaries between these plates, extraordinary things happen. Plates spread apart at mid-ocean ridges, where upwelling mantle material creates new oceanic crust. Plates collide, and one is forced beneath the other at subduction zones, where oceanic crust is pulled back into the mantle. Continents drift, mountains rise, ocean basins open and close. The climate-relevant aspect of all this is the carbon cycle. Carbon dioxide enters the atmosphere through volcanic outgassing at mid-ocean ridges and hotspots. Carbon dioxide is removed from the atmosphere through weathering of silicate rocks. When rain falls on silicate rocks, the carbon dioxide dissolved in the rain reacts with the rock minerals to form carbonate minerals, which are then washed into the ocean and eventually deposited as carbonate sediments on the ocean floor. At subduction zones, these carbonate sediments are pulled back into the mantle, where heat decomposes them and releases the carbon dioxide again into the atmosphere through volcanic activity. This is the long-term carbon cycle, and it operates on timescales of millions to tens of millions of years. The climate-stabilizing function of this cycle is profound. If the planet gets too warm, silicate weathering accelerates because chemical reaction rates increase with temperature, pulling more carbon dioxide out of the atmosphere and reducing the greenhouse effect, cooling the planet back down. If the planet gets too cold, silicate weathering slows because cold and ice reduce the exposure of fresh rock to rainwater, allowing volcanic carbon dioxide to accumulate in the atmosphere. increasing the greenhouse effect and warming the planet. It is a negative feedback loop, a thermostat that has kept Earth's surface temperature within the range that permits liquid water for most of the last 4 billion years. This thermostat is why Earth did not suffer the fate of Venus despite the sun brightening by 30% over the planet's lifetime. As the sun brightened, the system automatically adjusted more weathering, removed more carbon dioxide, reducing the greenhouse effect and compensating for the increased solar input. And it is why Earth did not suffer the fate of Mars. Mars lost its internal heat engine, lost its volcanism, lost its ability to recycle carbon, and eventually lost the balance of its carbon cycle. The thermostat stopped working. What fraction of rocky planets have active plate tectonics? We don't know because we cannot detect plate tectonics on exoplanets with current technology. The answer is probably not all of them, and possibly not most of them. Earth appears to be the only body in our solar system with active plate tectonics in the terrestrial sense. Venus has a stagnant lid, a single, immobile outer shell rather than mobile plates. Mars's tectonics appear to have been active early in its history and then shut down. The Moon and Mercury have no active tectonics. The conditions required for plate tectonics are debated, but they likely include a specific range of mantle viscosity, water content. Water appears to act as a lubricant that enables plates to slide and heat flow. Whether these conditions are common among rocky exoplanets or rare is, at the moment, an open scientific question. But the lesson of our own solar system is that of the 4 rocky worlds, only one has active plate tectonics today, and that one is the only one with a biosphere. The magnetic field and the plate tectonics operate invisibly, beneath the surface or beneath the ocean. They don't announce themselves. They are, in the most literal sense, hidden foundations. And they may be the filters that most of the planets that sit inside their star's habitable zone fail to pass. Part 9. When almost Earth isn't enough. It would be very convenient if the galaxy's most Earth-like candidates were obviously and clearly Earth-like. It would make the rest of this story a lot more straightforward, and honestly, it would make for a much more satisfying video. You'd expect that after 30 years of exoplanet science, after Kepler and TESS and the James Webb Space Telescope and thousands of ground-based hours of radial velocity measurements, we would have at least one world out there that we could point to and say, yes, that one. That one looks like home. But the honest reality of our current observational situation is that the planets which get labelled potentially Earth-like in press releases are, in almost every case, deeply ambiguous. And understanding why they're ambiguous is itself one of the most illuminating things you can do if you want to understand how many things have to be right simultaneously for a planet to actually deserve that label. Let's take the 3 most often cited Earth-like candidates and be ruthlessly honest about what we actually know. Proxima Centauri b, discovered in 2016, and immediately one of the most talked about exoplanets ever found, partly because of what it is, and partly because of where it is. It orbits Proxima Centauri, the nearest star to our own Sun, at approximately 4.2 light-years away. In cosmic terms, that is essentially next door. If you could somehow board a spacecraft travelling at 10% the speed of light, which is orders of magnitude faster than anything we've ever built, you'd arrive in about 42 years. So geographically, in the scale of the galaxy, this planet is practically in our backyard. Its orbital period is 11.2 Earth days, meaning a full year there passes in less than 2 weeks by our calendar. Its mass is estimated at roughly 1.27 times Earth's mass. Though the radial velocity method used to detect it gives us a minimum mass rather than an exact figure, the actual mass could be somewhat higher depending on the orbital geometry. It sits within Proxima Centauri's habitable zone, at a distance that could in principle support liquid water on its surface given a sufficiently thick atmosphere. And that is approximately where the good news ends. Proxima Centauri is a red dwarf, a flaring one. It regularly releases ultraviolet and X-ray bursts of extraordinary intensity events that would be catastrophic for any unshielded surface chemistry we'd recognize as life-supporting. Proxima b is almost certainly tidally locked, with one face permanently baked by starlight and the other permanently in darkness, separated by a terminator zone of perpetual twilight. Whether Proxima b has an atmosphere at all, whether one ever formed, whether the flaring has stripped it away over billions of years, whether what remains is anything thicker than the near vacuum on Mars is completely unknown. The James Webb Space Telescope has turned its instruments toward this system and has not yet been able to definitively characterize the planet's atmosphere. We know its approximate mass. We know its orbital period. We know it's close. Everything else, the temperature, the surface conditions, the chemistry, the internal structure, is inference and uncertainty dressed up as possibility. The TRAPPIST-1 system. If Proxima Centauri b is the closest candidate, TRAPPIST-1 is the most dramatic. 7 planets orbiting a red dwarf about 40 light-years away, all of them roughly Earth-sized by the transit measurements that revealed them. 3 of them, TRAPPIST-1a, F, and G, sit within the system's habitable zone, meaning 3 potentially rocky, roughly Earth-sized planets in the right temperature range around the same star. The system has been called the most Earth-like multi-planet system ever found, and in terms of sheer numbers of near-Earth-sized worlds packed into a habitable zone, nothing else in the catalogue comes close. When the system was announced in 2017, the excitement was genuine and justified. This looked, on the surface, like exactly the kind of thing we'd been hoping to find. But here is what actually happens when you look more carefully. JWST observations of TRAPPIST-1b, the innermost planet, have revealed thermal emission consistent with a bare rocker world with very little or no substantial atmosphere, absorbing and radiating heat the way a naked stone does, rather than the way a planet wrapped in an insulating heat redistributing atmosphere would. TRAPPIST-1c, the second planet, shows similar indications. The habitable zone, planets E, F, and G, haven't been fully characterized yet, and the story there is still being written by the telescopes. But the early results for the inner members of the system are sobering. If the planets closest to the star have already lost their atmospheres to the star's activity, the prospects for the outer planets aren't automatically good either. The star flares. All 7 planets are almost certainly tidally locked. The radiation environment that close to a red dwarf over billions of years is not gentle. The situation for life in the TRAPPIST-1 system is, at minimum, profoundly different from anything in our solar system, and it may be actively hostile to the kind of surface chemistry that produced us. Kepler 452b. This one gets called Earth's older cousin, which is a headline that writes itself and a description that deserves more scrutiny than it usually gets. It orbits a G-type star, a star similar in type to our Sun, which is already relatively unusual among the exoplanet candidates that attract attention, most of which orbit red dwarfs. Its orbital period is about 385 days, close enough to Earth's 365 that you can almost feel the similarity. And its host star is older than our Sun, about 6 billion years old, versus our Sun's 4.6 billion, which means if this planet is genuinely Earth-like, it has been sitting in its habitable zone for longer than Earth has existed. In principle, that extra time is time for biology to develop. Here is the problem. Kepler 452b has a radius about 60% larger than Earth's. That's a meaningful difference. And we do not know its mass because it was detected by the transit method. We saw it pass in front of its star, blocking a fraction of the starlight, which tells us its size. But without a mass measurement, we don't know its density. And without density, we don't know whether it's a rocky world with a solid surface or a mini Neptune with a thick gas envelope and no surface to stand on. Its radius sits uncomfortably close to the Fulton Gap, the statistical divide between planets that tend to be rocky and planets that tend to retain thick gaseous atmospheres. It could be on either side of that divide, and we genuinely don't know which. what its atmosphere looks like, whether it has liquid water, whether it has a magnetic field, whether anything resembling plate tectonics is operating on its surface, all of that is completely unknown. We have a radius and an orbital period. That is nearly the entirety of what we know about this world that headlines called Earth's cousin. And this is the observational reality that ties all three of these candidates together. We are extraordinarily good at detecting the size and orbital period of exoplanets. We are reasonably good at constraining mass and density when the geometry cooperates. We can occasionally extract rough atmospheric information from transmission spectroscopy, where starlight filtered through a planet's atmosphere as it transits. Its star carries chemical fingerprints that sensitive instruments can read. We have detected water vapor, carbon dioxide, methane, and other molecules in the atmospheres of exoplanets this way, though mostly in larger, puffier planets where the signal is stronger. But we cannot currently detect a planetary magnetic field from light years away. We cannot detect plate tectonics. We cannot observe ocean chemistry or mantle convection or core state. We cannot see whether a planet's axis is being stabilized by a large moon or wobbling chaotically through a 100-degree range. We are seeing the silhouette of the planet, its size, its orbit, occasionally a smeared spectral fingerprint of its outer atmosphere, and from that silhouette we are being asked to determine whether the full interior architecture, the one we've spent this entire video cataloguing as essential, is present. We are reading the shadow of a building and trying to determine whether the plumbing works. The full package, the right star, the right formation history, the Jupiter analog, the stabilizing moon, the habitable zone orbit, the active dynamo, the plate tectonics, the billions of years of climate stability cannot be confirmed or ruled out for any known exoplanet with current technology. We can check perhaps the first 2 or 3 items on that list for the best candidates. Everything after that is invisible to us at present. This is not a reason for despair. It is a reason for precision and for humility about what we're actually claiming when we call something Earth-like. When we say we haven't found another system that mirrors our own, we mean we haven't found one that we can confirm mirrors our own across all the parameters that matter. But we've also consistently found that the candidates which initially seemed most promising look considerably less benign the closer we examine them. The TRAPPIST-1 planets losing their atmospheres. Proxima b, sitting in a radiation storm. Kepler 452b, possibly not even being rocky. The chain we've been building throughout this video, every link of it remains unconfirmed elsewhere. And that silence in the data is itself a signal worth taking seriously. Part 10. The galaxy doesn't look like home. Let's take stock of what the full exoplanet survey actually tells us about how the galaxy distributes its planetary architecture, because the picture that has emerged from 3 decades of increasingly precise detection is about as far from the pre-1990s expectation as you could reasonably imagine. And I want to be careful here, because this is the part of the story where it's tempting to just list statistics and move on. But the statistics deserve to be felt, not just catalogued. Because what they're collectively saying is something that the scientific community of 30 years ago would have found genuinely startling. When astronomers in the early 1990s began theorizing about what a survey of exoplanets would eventually reveal, the working assumption almost universally held was that our solar system was broadly representative. You form a star, material collapses into a rotating disk around it, the inner disk builds rocky planets, the outer disk builds gas giants, everything settles into roughly circular orbits, and you get a configuration that looks, at least in its broad outlines, like home. The expectation was not that every system would be identical to ours. It was that ours would sit comfortably near the middle of the distribution, a typical outcome of a typical process. What we found instead was so different that it forced a complete rewriting of planetary formation theory, not once, multiple times. The most common planets in the galaxy, by every survey we have conducted, are sub-Neptunes and super-Earth's planets with radii between roughly 1.2 and 4 times Earth's radius. Not gas giants, not rocky Earth-sized worlds. Something in between, something that our solar system does not contain a single example of. These planets orbit the majority of Sun-like stars. They usually appear at short orbital periods, less than 100 Earth days, meaning they are packed in close to their stars, completing their years in weeks or months, rather than the 365 days we're accustomed to. They are often multiple systems with 3, 4, 5 of these worlds stacked inside the orbit that Mercury traces around our Sun. They are, in the most literal sense, the galaxy's default planetary output. If the universe is running a planet-building experiment, and you want to know what it most commonly produces, it produces these: compact, close-in, multiple, larger than Earth, but smaller than Neptune. Our inner solar system, 4 planets ranging from roughly 0.3 to 1.5 Earth radii, spread out across 1.5 astronomical units in well-separated, nearly circular orbits, represent something that the data consistently classifies as a minority architectural outcome. We are not the template. We are a particular result in a wide distribution, and we don't sit near the peak of that distribution. Now look at the dynamical behavior of other systems, because it's not just the planet types that differ, it's how those planets behave in their orbits. Systems showing evidence of past dynamical instability are common in the catalogue. Highly eccentric orbits, elongated ellipses rather than near circles, appear frequently. Widely scattered orbital inclinations, where planets in the same system orbit in planes tilted significantly relative to each other, are observed regularly. Evidence of former planets, now absent gaps in orbital spacing, resonant structures that imply a past occupant that was subsequently ejected, appears in a meaningful fraction of systems we examine carefully. The galaxy is full of planetary systems that went through violent rearrangements and never fully settled. The survivors of those rearrangements orbit in whatever configuration the chaos left them in. Our solar system, by contrast, is dynamically calm in a way that stands out. The planets orbit in nearly the same plane. Their orbits are nearly circular. The giant planets sit in a well-separated outer region. The rocky planets occupy a well-separated inner region, and the whole arrangement has apparently persisted in something close to its current configuration for billions of years. This is not the norm. This is the exception. And the reason it matters, the reason we've spent so much of this video tracing how it came to be, is that this calm, stable architecture is probably a prerequisite for the kind of long-duration habitability that produced us. A dynamically unstable system, reshuffling its planets every few 100 million years, is not a system that gives biological processes the time they need. Giant planet demographics add another layer to this picture, and this one is particularly instructive. Hot Jupiters, those massive, close-in gas giants that formed in the outer disk and then migrated all the way inward, destroying or preventing the formation of habitable inner planets along the way, appear around roughly 1% of Sun-like stars. That sounds small, but it represents billions of stars across the galaxy whose inner systems were likely cleared and rendered uninhabitable by a single migrating giant. Cold Jupiter's gas giants, at larger orbital distances, the category that includes our own Jupiter, appear around 10 to 20% of Sun-like stars. That number sounds more encouraging until you look at what's inside it. The cold Jupiter population is not uniform. A cold Jupiter in a highly eccentric orbit, one that swings significantly closer to and farther from its star over the course of each year, doesn't play the same constructive gravitational role that our Jupiter does. A cold Jupiter in an eccentric orbit periodically flings debris inward toward the inner solar system rather than deflecting it outward. It can destabilize the orbits of inner rocky planets over geological timescales. It can do more harm than good. The subset of cold Jupiters that are specifically in low eccentricity orbits, at the right distance. In configurations where they constructively shape the outer debris disk and protect the inner planets, rather than threatening them, that subset is substantially smaller than the 10 to 20% figure. How much smaller is uncertain, but the constructive Jupiter analog configuration appears to be the minority case within an already minority category. Detection bias is real, and intellectual honesty requires acknowledging it directly. The transit method that Kepler used to find most of its planets is heavily biased toward close-in planets. A planet transiting its star at 5 astronomical units, the distance Jupiter orbits our Sun, blocks the star's light for only a few days every 12 years. A survey running for 3 or 4 years will catch that transit at most once, if at all, making detection unreliable. The radial velocity method, which measures the gravitational wobble of a star as a planet orbits it, is also biased toward massive planets in close orbits, because those produce the largest and most frequent signals. So, we are almost certainly undercounting outer giant planets in the current catalogue. Our picture of how common true Jupiter analogues are is probably too pessimistic, because we're simply not well equipped to find them yet. But here is the critical point. Even after planetary scientists apply the best available corrections for these detection biases, even after they mathematically account for the planets we're probably missing and adjust the statistics accordingly, the picture does not transform into one where our solar system looks typical. The most thorough analyses of the corrected exoplanet catalogue consistently find that our architecture no super-Earths in the inner system, a Jupiter analogue in a low eccentricity outer orbit, a calm and well-separated arrangement of inner, rocky, and outer giant planets is unusual. The corrections move the needle. They don't move it to the center of the distribution. There is one more piece of the architectural puzzle that rarely gets discussed in popular accounts, and it lives in the outermost reaches of our solar system. Beyond Neptune, at distances of 30 to 50 astronomical units, our solar system maintains the Kuiper Belt, a disk of icy small bodies that serves as the source region for many short-period comets. Even farther out, at distances reaching perhaps 50,000 astronomical units from the Sun, nearly a quarter of the way to the nearest star, the Oort cloud is thought to exist as a roughly spherical reservoir of long-period comets, the outermost boundary of the Sun's gravitational reach. These structures were sculpted by the nice model rearrangement we discussed earlier, the late dynamical reshuffling of the outer planets that sent shockwaves through the entire system. Other solar systems have outer debris disks that are detectable in infrared emission. We can see the thermal glow of dust and icy material in the outer regions of nearby planetary systems. Their structures vary enormously. Some have vastly more material in their outer disk than our Kuiper Belt, implying bombardment rates for their inner planets that would be dramatically higher than what Earth has experienced over the last 3 billion years. The specific architecture of our outer solar system, the amount of material there, how it's distributed, how it interacts with the planets, is yet another parameter that varies from system to system, and that almost certainly matters for the long-term habitability of whatever rocky planets exist in the inner region. The overall picture assembled from all of this is consistent and, depending on your perspective, either sobering or fascinating. Our solar system is not the template from which other systems deviate. We are a particular outcome in a vast distribution of outcomes, and we sit in a region of that distribution that is not heavily populated. The galaxy runs the planet formation experiment on a staggering scale billions of times, across hundreds of billions of stars, and it generates an enormous variety of results. Hot Jupiters and compact super-Earth systems and dynamically chaotic arrangements and quietly stable outer giants. All of these appear in the data in varying proportions. Our specific result, the one we've been building a picture of throughout this video, does not appear among the most common outcomes. So the question becomes, exactly how uncommon is it? And answering that question requires doing something that sits right at the boundary between science and philosophy, taking each link in the chain, assigning it a probability, and multiplying. The number that comes out of the other end of that calculation is the thing that changes how you see the sky. Part 11. The multiplication that changes everything. Here is where we stop cataloguing individual conditions and start asking what happens when you put them all together. This is the part of the conversation that planetary scientists, astrobiologists, and philosophers of science have been circling for decades, and it produces a number that is either reassuring or alarming depending on how you look at it. Probably both, if you sit with it long enough. The idea itself is simple enough to state in a single sentence. If each condition in the chain that produced Earth is independently required, meaning you genuinely cannot skip any of them, that the absence of any single link breaks the entire chain, and each condition has some probability of being met in a randomly chosen planetary system, then the probability that all conditions are simultaneously met in the same system is the product of all those individual probabilities multiplied together. This is the conditional probability framework, and it is not exotic mathematics. It is the same logic you use when you calculate the odds of flipping heads 10 times in a row. Each individual flip has a 1 in 2 chance. The combined probability of 10 consecutive heads is 1 in 2 to the power of 10, 1 in 1024. The chain multiplies, and the longer the chain, the more unforgiving the multiplication becomes. This framework underlies something called the rare earth hypothesis, a body of thinking that was crystallized and brought to wide attention in a book published in the year 2000 by paleontologist Peter Ward and astronomer Don Brownlee, though the conceptual foundations had been built by many researchers over the preceding decades, and subsequent work by Joe Kirschvink and others has extended and refined it considerably. The central argument is not that Earth is the only planet with life. It is more specific and more careful than that. The argument is that the conditions required for complex, multicellular life, the kind of life that builds nervous systems and eventually telescopes, are far more demanding than the conditions required for simple microbial life, and that the full package of conditions required for the former may be genuinely, measurably rare across the galaxy. Let's walk through the chain we've built in this video and attach rough, illustrative probability ranges to each link. I want to be clear about what these numbers are and what they aren't. They are not hard empirical facts handed down from a completed census of the galaxy. They are order of magnitude estimates, informed by current data, carrying large uncertainties in both directions. Some of them are better constrained than others, but the exercise of multiplying them together is instructive and important, even if the individual values shift as science improves. Because what changes when the values shift is the magnitude of the answer, not its direction. Start with the star. We've established that the Sun is a G-type main sequence star, stable, long-lived, sitting in a favorable region of the galaxy, varying by less than 0.1% in luminosity over its activity cycle. The fraction of stars that meet this combined description, the right spectral type, the right stability, the right galactic address, sits somewhere between 5 and 10% of all stars. To be generous, call it 0.1, 1 in 10. Already, before we have said a single word about planets, 90% of the galaxy's stars are potentially eliminated from consideration. The filter begins at the very first step. Now add the requirement for a Jupiter analogue in the right configuration, a cold gas giant in a low eccentricity orbit at the right distance from its star, one that played something like the grand tack role in the system's formation, rather than migrating destructively inward and sterilizing the inner system. Based on current demographics of planetary systems around Sun-like stars, something between 5 and 15% of those systems appear to host a cold Jupiter of any kind. The subset of those cold Jupiters that are specifically in low eccentricity orbits at constructive distances, rather than the highly eccentric cold Jupiters that periodically fling debris inward, is smaller still. Being generous with the uncertainties, call this 0.1, another factor of 10 reduction. Now, add the requirement that the inner system produced rocky planets in the habitable zone with low orbital eccentricities and without the super-Earth formation that dominates most other systems. This is the outcome of a specific formation history, the grand tack working correctly, Jupiter's migration reversing at the right moment, the inner disk being sculpted rather than flooded with building material. What fraction of systems with a Jupiter analogue in the right configuration also produce this specific inner system architecture? The honest answer is that we don't know precisely, but based on the rarity of systems that appear to have this configuration in the surveys we've conducted, a reasonable estimate is somewhere between 10 and 20%. Call it 0.15. The giant impact that produces a stabilizing moon, the fraction of rocky habitable zone planets that experience a collision of exactly the right size, at exactly the right geometry, producing a debris disk that coalesces into a moon large enough to stabilize axial tilt over billion-year timescales rather than a smaller moon that provides partial stabilization, or a collision that produces no stable moon at all, or an impact at the wrong angle that strips the atmosphere, instead, is estimated by researchers who have modeled these impact scenarios at perhaps 5 to 10%. Call it 0.07, an active magnetic dynamo maintained over billions of years. The fraction of rocky habitable zone planets that sustain an active geodynamo keeping their outer core liquid, driving convective currents that generate a protective magnetic field for the several billion years that complex life apparently requires, is genuinely unknown because we cannot measure core states on exoplanets. But our own solar system gives us a data point. 1 in 4 rocky planets currently has an active global dynamo. Mars lost its dynamo roughly 4 billion years ago. Mercury has a weak one. Venus has none detectable. Only Earth has maintained a full, robust field. 1 in 4 is not a small number, but it applies to a sample of one solar system, which is a sample size that should make any statistician nervous. Call it 0.25, acknowledging the enormous uncertainty in that estimate. Active plate tectonics operating over geological timescales. Our solar system is again 1 in 4. Earth has active plate tectonics, and Venus, Mars, and the Moon do not, at least not in any form resembling Earth's mobile lid regime. The fraction of rocky habitable zone planets with long-lived active plate tectonics has been estimated by various researchers at somewhere between 10 and 30%, depending heavily on assumptions about mantle viscosity, water content, and heat flow. Call it 0.2. Now multiply all of those together. 0.1 times 0.1 times 0.15 times 0.07 times 0.25 times 0.2. The product is approximately 5.25 times 10 to the power of -6. Roughly 1 in 200,000, even being generous with several of the individual estimates and leaving out additional filters, the right surface water fraction, the right early chemical inventory, the long-term orbital stability that would each reduce the number further. 1 in 200,000 in a galaxy of 200 billion stars, which means, if the math is in the right ballpark, something on the order of 1 million systems in the Milky Way might complete the full chain. 1 million sounds like a lot. It sounds like the story has a happy, populated ending. But hold that feeling for a moment and look at what happens to it when you probe the uncertainties. If each of the individual probability estimates I used is off by a factor of 2, if the actual probabilities are each half of what I called them, the product doesn't halve. It doesn't even reduce by a factor of 10. It drops by a factor of 2 to the sixth power, which is 64. 1 in 200,000 becomes roughly 1 in 13 million. Now you have perhaps 15,000 such systems in the Milky Way rather than a million. Tighten each estimate by a factor of 5 rather than 2, which is well within the uncertainty range for several of these values, and the product drops by 5 to the sixth power, which is 15,625. 1 in 200,000 becomes 1 in more than 3 billion. At that end of the uncertainty range, systems like ours might be so rare that the observable universe containing something like 2 trillion galaxies contains only a handful of them, or fewer. This is what scientists mean when they talk about being sensitive to assumptions. The difference between a universe full of Earth-like systems and a universe containing almost none is entirely contained within the uncertainty bands on these individual probability estimates. We are not yet able to measure most of these probabilities precisely enough to distinguish between those two universes. There is a deeper wrinkle still, and it is the most philosophically interesting one. The assumption, threading through all of this calculation, is that the individual conditions are independent of each other, that the probability of having the right star is unrelated to the probability of having active plate, tectonics for instance. But this is almost certainly not exactly true. There may be correlations in both directions. A protoplanetary disk with the right composition to produce a Jupiter analogue in the right location may also be more likely to produce inner rocky planets with the right water content for plate tectonics. Or systems that form Jupiter analogues early may systematically clear their inner disks in ways that produce dry, less geologically active rocky planets. The correlations, if they exist, could push the overall probability up or down from the naive multiplication, and we don't yet have the data to measure them. And then there is the anthropic selection effect, which is the piece of this puzzle that is hardest to hold in your head correctly. We exist inside one of the systems that completed the chain. That is not a coincidence, it is a logical necessity. You cannot observe the universe from inside a system that failed to produce observers. This doesn't mean the chain is common. A single lottery winner standing in the winner's circle cannot conclude from their own presence there that lotteries are easy to win. What they can conclude is that somebody was always going to win, and they happen to be that somebody. The selection effect tells us we will always find ourselves inside a successful outcome. It doesn't tell us how many successful outcomes exist. What the multiplication exercise tells us, even wrapped in all its uncertainties, is that the chain is long and each link costs something. The cost per link might be small, it might be large. It is probably different for different links, and we currently know the costs only very roughly, but they multiply. And the total cost, the full probability of the complete chain completing in a randomly chosen system, is almost certainly much lower than intuition suggests when you look at the night sky full of stars and think, surely this is everywhere. It may be, or it may not. Right now, we genuinely cannot tell. And that uncertainty is not a failure of science, it is the frontier of it. The answer to how much the chain costs is one of the most consequential open questions in all of human knowledge. Because the answer tells us something that nothing else can, whether the silence out there is emptiness or just distance. Part 12. The night sky as a sample size. Let's go back to where we started. You're in a chair. There's a sky overhead, or a ceiling if it's cloudy, or a roof if it's nighttime and you're inside. But conceptually, the sky is there, always there, and beyond it, the stars. And every one of those points of light, or the vast majority of them, is a sun, not a decoration, not a backdrop. A star, with its own gravitational field, its own history stretching back billions of years, its own collection of worlds orbiting it in patterns that differ, almost certainly, from the pattern we orbit in. Each one of those points of light is the center of its own system, running its own version of the planet formation experiment, producing its own particular result. And we now have enough data to know that those results vary enormously, and that our result is not the common one. We didn't know that 30 years ago. We suspected it, in the way that scientists suspect things before the data arrives, with a combination of theoretical expectation and genuine uncertainty about whether those expectations would hold. The confirmation of exoplanets around Sun-like stars came in 1995, when Didier Queloz and Michel Mayor, using the radial velocity method at the Haute-Provence Observatory in France, detected 51 Pegasi b, the hot Jupiter, that appeared in the first part of this video and that rewrote the textbook on planetary formation the moment it was confirmed. The discovery earned both men the Nobel Prize in Physics in 2019, shared with cosmologist James Peebles. It was recognition not just of a single detection, but of the fact that this detection had genuinely, permanently changed how humanity understands its place in the universe. Before 1995, the existence of planets around other stars was a reasonable theoretical expectation, but an observational blank. After 1995, it was a confirmed reality, and the specific nature of what was confirmed immediately suggested that the reality was stranger than the expectation. In the 30 years since that first detection, the pace of discovery has been extraordinary in the most literal sense of that word. The Kepler Space Telescope, launched in 2009 and retired in 2018 after running out of fuel, surveyed more than 150,000 stars simultaneously and found thousands of planetary candidates, the majority of which have been confirmed. The TESS mission, launched in 2018, extended the survey across a larger fraction of the sky with different detection sensitivities. Ground-based radial velocity programs have continued refining masses and orbital parameters. The James Webb Space Telescope, operational since 2022, has begun characterizing exoplanet atmospheres with a precision that was genuinely impossible before it existed. The result of all of this instrumentation, all of this observational time, all of this data processing, is a catalogue of more than 5,500 confirmed exoplanets as of 2025, with thousands more candidates awaiting confirmation. Statistical extrapolations from the confirmed sample suggest that the Milky Way probably hosts somewhere between 100 billion and 400 billion planets in total, more planets than stars, because many stars host multiple planets simultaneously. The night sky overhead, viewed through this lens, is not a backdrop, it is a sample size. Billions of planetary systems in various stages of formation, evolution, stability, and in some cases destruction, each one a data point in the galaxy's ongoing experiment with planet formation. Every possible variation on every parameter we've discussed in this video is being run simultaneously, somewhere out there. Different stellar masses producing different radiation environments. Different disk compositions producing different planetary building blocks. Different formation timescales, allowing or preventing the kind of resonance-driven migration reversal that shaped our outer solar system. Different late dynamical phases, some violent, some calm, and some intermediate. Different collision histories. Different volatile inventories. Different stellar activity levels bathing different planetary surfaces in different radiation environments over different timescales. The galaxy is not running one experiment. It is running billions of them in parallel, and the results it's producing are catalogued in our databases. And when we ask how many of those billions of experiments produced an outcome like ours, the honest answer, as of right now, is that we think it's a small fraction, but we don't know exactly how small. That uncertainty is real, and it matters, and we'll come back to it. But first, let's hold the full chain in view one more time, because I think it's only when you see all of it simultaneously that the weight of what we've been building throughout this video actually lands. The Sunday A stable, long-lived G-type star in a quiet region of the Milky Way, outputting energy with a consistency that varies by less than 1/10 of 1% over an 11-year cycle, sitting in a galactic neighborhood where supernova rates are low and heavy elements from previous stellar generations were available to build rocky planets, representing perhaps 7 to 8% of all stellar types, already a minority, before we've said anything else. A solar system formation history that involved Jupiter, a planet 318 times, Earth's mass migrating inward from its formation location in the outer disk all the way to approximately 1.5 astronomical units well inside the current orbit of Mars, and then reversing course and retreating back to the outer solar system. A reversal that required Saturn to form at the right time, in the right location, to establish a precise gravitational resonance with Jupiter that changed the direction of both planets' migration. A dynamical event that cleared the inner solar system of the super-Earth building material that dominates most other planetary systems, and that sculpted the asteroid belt into the relatively sparse ring of rocky debris it is today, and that starved the Mars-forming region of mass and left Mars as the small, geologically quiet world it is. A Jupiter analects, the end product of that formation history, sitting in a nearly circular orbit at 5.2 astronomical units, deflecting comets and asteroids from trajectories that would otherwise bring them into the inner solar system at rates that might have prevented the development of a stable biosphere, representing, in the current exoplanet catalogue, a configuration found in perhaps 6 to 10% of Sun-like star systems, and in the correct orbital configuration for constructive rather than destructive gravitational influence in a smaller fraction still, a giant impact 4.5 billion years ago, when a Mars-sized body designated Theia struck the proto-Earth at an oblique angle, shearing off material that coalesced into the Moon, a moon large enough and at the right orbital distance to gravitationally stabilize Earth's axial tilt within a range of roughly 2.5 degrees over cycles of tens of thousands of years, preventing the kind of chaotic tilt variations over millions of years that Mars has likely experienced, and that would make long-term climate stability on Earth impossible. A habitable zone orbit at 1 astronomical unit that has remained dynamically stable over the full 4.6 billion years of the solar system's existence, neither drifting inward into a runaway greenhouse regime nor outward into permanent glaciation, maintained in its near-circular path by the gravitational architecture of the surrounding system. A planetary interior that has maintained a liquid iron outer core, kept liquid by the slow crystallization of a growing solid inner core, releasing latent heat and driving convective currents for at least 3.5 billion years, generating a magnetic field strong enough to deflect the continuous solar wind and prevent the atmospheric erosion that stripped Mars of most of its atmosphere after its own dynamo shut down roughly 4 billion years ago. Active plate tectonics that have been cycling carbon between the atmosphere, the ocean, and the mantle for billions of years through the silicate weathering feedback loop to a planetary thermostat that automatically removes carbon dioxide from the atmosphere when temperatures rise and allows it to accumulate when temperatures fall, compensating for the 30% increase in solar luminosity over the Sun's lifetime and preventing Earth from suffering the fate of Venus on one side or Mars on the other, and time, 4.6 billion years of it. Enough time for chemistry to organize itself into self-replicating molecules, for single-celled life to colonize every available niche, for the great oxidation event to transform the atmosphere, for multicellular complexity to emerge, for the Cambrian explosion to diversify animal body plans, for intelligence to develop, and for that intelligence to eventually look up and start asking questions about the chain of events that produced it. Every one of those elements is a real, documented, measurable feature of our solar system. Every one of them has a non-trivial probability of being absent in a randomly chosen planetary system. And the product of those individual probabilities, whatever the exact numbers turn out to be, and we discussed in the last section, How sensitive that product is to the specific values is the frequency of systems like ours in the galaxy. Here is what I find most intellectually compelling about where all of this leaves us, and where I want to leave you tonight. There are two completely opposite conclusions you can draw from everything we've covered, and both of them are defensible, and we genuinely cannot currently distinguish between them with the data we have. The first conclusion is that systems like ours are genuinely rare enough that complex life that requires this specific architectural package over these timescales, is a rare outcome in the universe. Maybe not completely unique. The numbers, even at pessimistic estimates, probably allow for some number of Earth-like systems in the Milky Way, perhaps thousands, perhaps millions, depending on where in the uncertainty range the true probabilities fall. But rare enough that the average distance between such systems is large, and rare enough that the silence from the cosmos, the fact that after more than 6 decades of searching with increasingly sensitive instruments, we have found no convincing, confirmed evidence of technological civilizations elsewhere is not surprising. The rarity of our architecture is, in this reading, the answer to Fermi's paradox. Where is everybody? They're not there, or they're so infrequent that the distances between them are too great for any signal we've sent or received to have bridged. The conditions that produce complex life almost never arise, and the universe is mostly, in terms of minds and civilizations, empty. The second conclusion accepts the rarity of our specific architecture, but challenges the assumption that our architecture is the only viable one. Life, in this view, is not so fragile and specific that it requires every element of the Earth system to be in place simultaneously. Life might emerge, and might even develop complexity in environments radically different from ours. The subsurface oceans of Europa and Enceladus, heated by tidal flexing rather than stellar radiation, shielded from space by kilometers of ice, dark and pressurized and chemically active, these are plausible habitats for microbial life, and possibly for more. Super-Earths, with thick hydrogen atmospheres, might maintain liquid water on their surfaces, even at distances far outside the conventional habitable zone, because the pressure of a massive atmosphere can raise the boiling point of water dramatically. Worlds around red dwarfs might have found solutions to the tidal locking and flaring problems that the current models suggest are insurmountable atmospheres that redistribute heat efficiently, magnetic fields generated by different mechanisms, biochemistries that tolerate radiation levels that would be lethal to Earth life. The specific conditions that produced us might be one path to complexity rather than the only path. And if life is adaptable enough to find many paths, then the galaxy's abundance of planets, even if most of them lack our precise architecture, means that life, in some form, might be widespread. Both of these conclusions carry their own emotional weight, and I don't think either of them is comfortable in the way that the pre-exoplanet expectation got solar system tonkel, and therefore life is common, and therefore we're probably not alone, was comfortable. The first conclusion confronts us with potential isolation on a scale that is difficult to fully process. The second conclusion is more hopeful about life in general, but it doesn't necessarily make us less alone, because life in the subsurface ocean of an ice moon, or in the atmosphere of a super-Earth around a red dwarf, is not life that builds radio telescopes and wonders about the universe. The question of whether we are cosmically alone depends not just on whether life exists elsewhere, but on whether complexity and intelligence exist elsewhere, and those are harder to achieve by any path. What the exoplanet data has genuinely done, and this is perhaps its most important philosophical contribution, is remove the comfortable middle ground that the pre-1995 expectation offered. We can no longer assume that our solar system is typical, that our conditions are the default outcome of planet formation, that what happened here probably happened everywhere. The evidence pushes back against that assumption too firmly and too consistently. We are unusual. the specific combination of stellar type, formation history, giant planet configuration, moon origin, dynamo longevity, and tectonic activity that we sit inside is not what the galaxy most commonly produces. We are in the tail of the distribution. The question is how far into the tail we sit and what that implies. Future instruments will push that question further toward an answer. The next generation of extremely large ground-based telescopes with primary mirrors 30 to 40 meters across, capable of collecting light that current facilities can't even reach, will dramatically improve our ability to directly image rocky planets around nearby stars. Improved space-based spectroscopy missions will measure atmospheric compositions on Earth-sized worlds with a precision that JWST can only approximate. We will be able to detect oxygen, carbon dioxide, methane, water vapor, and ozone in the spectra of habitable zone rocky planets. Atmospheric biosignatures, chemical combinations that are thermodynamically unstable and can only persist through continuous biological replenishment, may become detectable within decades. We may have, within the lifetimes of people watching this video, our first real observational evidence about whether atmospheric chemistry resembling Earth's is common or rare among rocky habitable zone planets. That data will not answer everything. It will not tell us whether those planets have magnetic fields or plate tectonics or large stabilizing moons. Those parameters will remain invisible for much longer, perhaps until technologies we haven't yet imagined are developed. But it will begin to answer the most fundamental version of the question we've been circling all night. Is the chemistry of life common, or is it rare? Is biology a predictable outcome of the right physical conditions, or is it a contingent result of a chain of events that could have gone differently at any step? And maybe the most remarkable thing about all of this is the viewpoint from which we're asking the question. The chain of contingencies that had to align to produce us the specific star, the specific formation history, the specific impact, the specific planet, the specific interior also produced, as an apparent byproduct, creatures capable of recognizing the improbability of their own existence and designing instruments sensitive enough to test it. We went from a collapsing molecular cloud to a civilization with radio telescopes and space observatories in 4.6 billion years. We reconstructed the formation history of our solar system from isotopic ratios in ancient rocks and the orbital resonances of distant planets. We detected the atmosphere of a world 40 light-years away by measuring the color of starlight filtered through a few hundred kilometers of gas. We are, in some sense, that feels important, even if it's hard to state precisely, the solar system's method of understanding itself. The universe generated the conditions for curiosity, and curiosity turned back and started mapping those conditions. Whether that recursive loop matter becoming complex enough to examine the conditions of its own complexity is a common outcome in the universe, or a rare one, is the question the next century of astronomy will begin to answer. For now, the data sits where it sits. 5,500 confirmed worlds, more than 4,000 systems examined, no confirmed architectural twin of our solar system anywhere in the catalogue. A galaxy almost certainly containing hundreds of billions of planets, and among all of them, this specific configuration, quiet star, stable orbit, reversed migration formation history, outer giant in the right place, catastrophic impact producing exactly the right moon, active interior generating an invisible shield, tectonic plates running a carbon thermostat for billions of years, appearing to be genuinely, measurably, uncomfortably rare. The night sky is not a mirror of home. It is a reminder that what happened here was specific, contingent, the product of a chain that could have broken at any link and, based on everything we've observed, usually does. You are not sitting under a typical sky. You are sitting under the sky of a system that step by step and billion by billion years managed to complete a sequence that most systems apparently do not. The universe has been running this experiment for 13.8 billion years across hundreds of billions of galaxies, each containing hundreds of billions of stars, generating trillions upon trillions of planets in every configuration the laws of physics permit. If the architecture that produced you is 1 in a million among all those worlds, then millions of places like this exist, and the universe is richer than we know. If it is 1 in a trillion, then the silence out there is not emptiness. It is the sound of an experiment that almost never reaches this particular conclusion. Either way, the sky above you is not ordinary. It never was. You just needed 30 years of exoplanet data and one long night of following the chain all the way to the end to finally see it clearly.